And you didn't bring me any.
You can't eat that.
No, I can't. You're right, but you didn't bring me any.
Good morning, Mr. Kane.
Good morning, Mrs. G. It's not actually morning, it's afternoon.
I know, but I'm so used to saying good morning now, I'm not changing.
They don't like it when we talk about this stuff anyhow, so let's just go straight into resonance.
All right, resonance structures.
Resonance structures, okay. It turns out that we've done multiple bonds, and it turns out that you can have multiple bonds and single bonds, and it can sometimes be difficult to tell where they go.
Okay.
All right. For instance, with ozone here.
Okay.
Ozone's got a double bond and a single bond, and it can be kind of difficult to figure out which one to draw.
Yeah, because if I want my double bond on the right, and I've got the right number of electrons, and I've got the octet rule established, but you want a double bond on the left, that's not to say my structure's wrong and yours is right. They're both adequate structures of the same compound.
Now, my understanding of the word resonance, when I pluck a guitar string, it resonates, right? It kind of vibrates back and forth.
Mm-hmm.
Is it true, then, that ozone kind of vibrates back and forth, the double bond?
That second line is technically a delocalized pair of electrons that will spend 50% on the right, 50% on the left.
So it'll keep moving back and forth?
Yes.
Between the
central
central oxygen?
Pair of electrons, yep. Pair of electrons. In a double bond, it's a pair of electrons. In a triple bond, it's two pair of electrons that will move around.
But the point is that both these answers are right.
Both these answers are correct, and resonance usually revolves around a double or a triple bond.
And
usually doubles.
And it would be more correct to draw both of them and draw an arrow between.
That is correct.
Okay, all right, that sounds good. So to summarize that, when you can't tell where the double bond goes, you draw both structures, and you use a double-headed arrow in between them to indicate that the structure resonates between two extremes. Now, if there's two ways to draw it. If there winds up being three ways to draw it.
Well, just imagine a double. Just imagine a double bond on something like NO3. If there's a double bond between the one nitrogen and the oxygen, then there can be a double bond between the nitrogen and the other oxygen, and
the nitrogen and the other oxygen.
That's
yeah.
three structures.
Yeah. Okay.
Polyatomic ion notation. Ooh, the polyatomics. Gosh, remember learning those?
Nitrate, phosphates.
Sulfate, sulfite, hypochlorite, perchlorate.
Carbonate.
Oh my.
That's what Han Solo was frozen in.
Carbonate. That was a long time ago.
It was in a galaxy far, far away.
Far away. If an ion is diagrammed, ions are placed in square brackets. The charge is outside of the bracket as a superscript.
So it's just like doing a single ion, single atom ion.
Yeah,
it's
like
just that
you
you've
showed
got a
earlier.
polyatomic.
Yeah. The total number of valence electrons is affected by the charge.
So if it says it's a 2 negative charge,
you added 2.
You added 2 electrons. If it's a 1 positive charge,
you took 1 away.
Okay, that makes sense. So
look at that, SO4.
Yeah, there's the example of it.
Yeah.
If I was doing this as an exercise,
in order. Step number 1, tally up the number of valence electrons.
Okay.
Sulfur is in family number 6, along with oxygen, so that's technically 5 times, right?
Yeah.
5 times 6.
I did 6 plus 24.
Yeah, there's
yeah.
30, plus the 2 from the charge. That's 32 valence electrons in this structure.
Right. Okay, so 32 valence electrons.
Pick your central atom.
Sulfur. It's the only. It's a lone man kind of deal.
Attach the terminals to the central atom. They're branching off.
And by doing that, I've just used 8, so now I've got 24.
Distribute the remaining electrons on the terminals first. If there are any left over, they go on the central atom.
18. 12.
And you already can tell that 12 is going to work.
Yeah, I can tell it's going to work perfectly.
Yeah.
We've done enough of these that I can tell almost right away.
There's no double bond.
No double bonds. Now, this is an ion, so since it's an ion,
put it in brackets.
I need to put it in a square bracket, and I need to put the charge on the outside.
Yep. And it's done. You got the 32 electrons. Oxygen and sulfur both achieve an octet rule. Finished.
Okay.
Nothing else to be said.
Let me ask you this, Mrs. G. What if I wanted to try and show what lithium sulfate looks like?
You would draw 2 lithium ions.
Okay. So here's a lithium ion here. And it's a positive charge. And there'd be another lithium ion, right? Would I want to draw the other lithium ion over here?
Nope.
Probably not,
Be
right?
attracted to it. Opposites attract.
Right, opposites attract. So I probably want to put it on the opposite side over here.
Yep.
All right, so lithium ion with a positive charge on it.
Yep. And then, of course, there'd be one at the top because it's a crystalline structure. Salts are crystalline structures.
Oh,
typically.
yeah, this would be a repeating structure.
It would be a repeating structure.
Yeah. Uh-huh. All right.
Very elaborate.